Hello everyone, welcome to my YouTube channel. Here in this presentation, I am going to make you people understand one of the important principle of green chemistry, which is the use of safer solvents and auxiliaries. But before we proceeding directly to this principle, let us first understand the concept of green chemistry. The green chemistry was actually introduced by Paul Anastas, who is also known as father of green chemistry. His philosophy was sweet and simple that it is an ethical responsibility of a chemist to synthesize new chemistries in an environmentally benign manner. And in this way, the industrial and societal cost of action to improve environmental protection can be reduced. The green chemistry aims to keep the hazardous material out of environment in the very first, and it is the designing of chemical processes in such a manner to either eliminate or to reduce the use of hazardous substances in a chemical synthesis. Now, what actually this principle states, it states that whenever it is possible economically and technically in a chemical process, the use of solvents should be avoided, and in case it can't be, then we must approach for a solvent which is eco-friendly in nature. We see that usually huge amount of solvent are being used in the synthesis of chemicals, and most of these reactions are carried out in organic solvents, which are volatile in nature mostly, and it's really a matter of concern because they are an important factor in safety of a product, and they have environmental impact also. Now the problem that lies with these organic solvents, here I have mentioned in my slide. Some of the problems include, like, they are expensive in nature, they are volatile in nature, flammable and carcinogenic even. Then they can cause bad health effects like eye irritation, skin burn, allergies, and even ozone layer depletion. Now my topic also include a term called auxiliaries. What are they actually? Actually, these are not direct part of a chemical reaction, but they aid in the synthesis of our desired product. Uh, their example includes separating agents. We make use of these agents in solvent extraction purposes, for example, uh, like in caffeine extraction process. So then solvents we use for recrystallization purposes, then dispersing agents. All these fall in the category of auxiliaries only. What's the safer option available to us? The foremost thing is we must try to avoid solvent as much as possible, and if we fails to avoid the solvent in certain reactions, like where we need to homogenize a reaction mixture completely, then there are heat transfer problems. Then green chemistry tells us that we must approach for a solvent which which should have at least following properties, like it should be easily accessible to us, it should be non-toxic, inexpensive, recyclable, and can be easily removed from a product. It should be non-carcinogenic and less volatile even. Now the greener approaches that are available to us, first is water. Water, as you know, it is available everywhere and it's a universal solvent. Although the problem with water is that majority of organic compounds are insoluble in it, but this problem can be resolved by the use of certain foreign substances in it, like surfactants and phase transfer catalysts. Now, the important thing I have mentioned here, that why water can be a replacement for volatile organic solvents. Uh, as we increase the temperature of water, its ionic product start increases, and at the same time its polarity decreases. So it can be used as a replacement here, and it has been found experimentally that at temperature over 200 degrees Celsius, water start to take properties of organic solvents. Like example here I have included that at 300 degrees Celsius water has properties almost similar to acetone. Then water nowadays is also used for as a solvent for coatings. Most of the water-based paints use copolymers of polyvinyl acetate, although they do contain small amounts of organic solvent, but the amount of volatile organic emissions and health risks are minimal in this approach. So water has unique properties with it. Then the second option available to us is the use of supercritical fluids. What are they actually? Uh, these supercritical fluids are formed when certain substances or compounds like carbon dioxide or water even when they are subjected to a temperature and pressure higher than their critical point, then they resulted in the formation of supercritical fluids. And at this stage, these compounds present in a single phase only and possess properties of both liquid as well as gaseous phase. Example supercritical CO2, and it find its use as an extraction solvent, dry cleaning, and many more. The important thing here is the carbon dioxide released from its use as solvent doesn't have net contribution to global warming. So it's a good approach. Then third option available to us is use of ionic solvents. If we try to understand the ionic solvent in a broader sense, then they can be viewed like common ionic materials such as sodium chloride. The difference being that these ionic solvents are liquid at room temperature, and the probable reason can be due to poor packing of respective ions. The major advantage of using ionic liquids as solvent is because of their low vapor pressure and which can offer us economic benefits as well. The ionic solvents can act as both catalyst as well as solvent as at the same time, and these liquids give us a hope in replacing organic solvents which are, as we have discussed, hazardous and non-eco-friendly. These ionic solvents can be used in certain reactions like Diels-Alder reaction, uh, Riedel-Crafts reaction, etc. Some of the common ionic liquid that I have pasted here in this slide, you can see. Uh, then the next option available to us is the use of microwaves as a greener replacement for solvent-assisted reactions. Uh, we usually prefer the use of microwave radiations because these microwave assisted reactions requires no use of solvent, or they can even reduce the volume of solvents to be used, and it's a one pot synthesis and takes very less time. One of the example that I have included is the synthesis of copper phthalocyanine complex. It's an important complex, and traditionally it was synthesized, uh, and its synthesis involved the use of high boiling solvent like nitrobenzene or trichlorobenzene, which are not at all good solvent for us. And but the green chemistry uh, offers us alternative, that is the solvent-free synthesis by making the use of these microwave radiations. And in this approach, we mechanochemically mix all the reactants in a mortar and pestle and then irradiate the resulted powdered mixture to microwave radiations. So you can see the use of high boiling solvent has been eliminated here. Now, here is a table I have mentioned the source from where I have collected this table. It is also mentioned here, and the table include here on the left hand side the undesirable left solvents, which are not good solvents, and on the right hand side these are the greener alternatives available to these red solvents. For pentane, it can be replaced by heptane. Similarly, hexane can also be replaced by heptane. The problem with these red solvents are as follows. Pentane has very low flash point, and good alternative heptane is available to this pentane solvent. Similarly, hexane, it is more toxic than alternative heptane, and it has been classified as a hazardous air pollutant in the United States. Similarly, other examples are also available here. Here I will end up my presentation by saying thank you for your attention and thank you very much.